today we talk about one more data structure about trees. It is the last data structure about trees. We have 2 more lectures. We'll cover some other topics other than trees, because everybody is kind of tired of trees. But this is the last lecture about trees. Today we discuss centroid decomposition. So what is centroid decomposition and when do you need to use centroid decomposition? There are 2 types of tasks when you may need centroid decomposition. We'll discuss both of them. First type of tasks is something like that. You want to look on all you have some tree. Let me draw some tree. I just like to draw trees. So you have some tree, and you want to make the following. You want to look on all possible paths in this tree. So you want to look on all pairs UV, and look on all these paths, and for all these paths calculate something, just to calculate number of some good paths, or calculate the optimal path along all possible paths in the tree, something like that. Let's solve something simple. So just to show you the technique, I will solve a very simple task. In this task, you want to calculate the number of possible pairs UV such that let's see number of pairs UV such that distance from U to V is no more than D. Exactly this problem can be solved without centroid decomposition, actually. You can solve this problem by just making a recursive procedure which when you transfer the elements from smaller set to the bigger set, something like that. I don't know the correct name for this technique, but actually exactly this task can be solved without centroid decomposition. But I will solve it using centroid decomposition just to show you how to implement centroid decomposition. So what is centroid decomposition and how to use centroid decomposition to solve tasks like this? Basically what you need is to make something like divide and conquer algorithm. So we will try to apply divide and conquer technique to the tree. Small to large merging. Is it the name? Okay. It's a nice name. It's self-explaining. I like that. Now, what I will try to do, I will try to apply divide and conquer technique to solve this problem. So you have this tree. I will fix one of the nodes of this tree. Let's say I have. Let's use this tree. So let's pick one vertex of this tree. Let's say this vertex. And now I will split all possible paths into classes. First of all, let's look on all paths which do not cover this vertex C. So if I have some path from U to V, and this path do not include this node C, then this path is inside one of these subtrees. So if I have path from U to V, and this path doesn't include this node vertex C, then this path is completely inside one of these regions. Yeah. So if U and V are both inside one of these regions, then this path does not include this node C. And now I need to consider only the paths which goes through this node C. So if the path is includes this node C, then I will split this path into 2 smaller paths. So if I have some path from U to V like this, then so the path from U to V goes through this vertex C. Then this path can be split into 2 segments. So I will have segment from U to C like this, and another segment from C to B, like this. That's the whole plan. Now, what I will do, I will pick one of the vertices of my tree, remove this vertex from the tree. The tree will be split into some subtrees. Now, for each of these subtree, I will call the recursive procedure. So I will recursively calculate the number of good pairs in each of these subtrees. And now, in the end, I will calculate the number of vertices which such that the path includes vertex C. To calculate paths like this, I will split this path into two parts, and then calculate number of paths like this using another special technique. So, again, what you need to do? First, you pick some node C. Then you split your tree into some parts. Recursively call the same procedure in all these subtrees. Then, in the end, you want to calculate the paths which includes node C. So, how to calculate these paths including node C? Well, let's see. We have this node C. We have these subtrees. What? No, you're too fast. It's not like this, but it's somewhat close. It's not always split in 3 parts. Sometimes it may be split in 2 parts or in 4 parts. It's just in this tree I split the tree into 3 parts, and they are not exactly the same size. Let's wait a little. So now I want to calculate number of pairs UV. Now let's use the same markers again. So I want to have vertex U here and let's say vertex B here. And the sum of these distances, this distance plus this distance, should be no more than D. So how to calculate number of such pairs? Well, what we can do, we can calculate the distance to all vertices. So we just call that first stretch from this vertex C and calculate distances from C to all nodes in this tree. Let's say D of V is distance from C to V. We can pre-calculate all these distances in linear time. We just start the recursion from node C and calculate distances to all nodes in this subtree, right? Now, when you pre-calculate these distances, what you want to do? You want to find number of pairs UV such that distance to V plus distance to U is no more than D. Now, if you fix one of these vertices, so for example, if you fix node U, then how to find node V? Node V is such node that distance to V is no more than D minus distance to U. So what we'll try to do, we'll fix one of these nodes, we'll fix node U, and for each node, we will find all possible nodes V such that this sum of these two distances is no more than D. So how to do it? Very easily. One of the small problem is that we need to find the number of pairs such that this U and V belong to the different subtrees. So it's a little bit more complicated. So we don't need to find all possible pairs, but we need to find all pairs which belong to different subtrees. Yeah. But let's forget about it for a minute. If we just want, let's solve this problem. For example, you have some array, yeah? So you have some array D. And you want to calculate number of pairs UV such that DU plus DV is no more than D. So how to calculate this? Pretty simple actually. What you can do again, you iterate all node V, you fix some node U, fix some element of your array, and now you need to find number of nodes V such that distance to V is no more than D minus DU. How calculate number of such nodes? Pretty simple. You can just do binary search. Yeah, you sort this array, and then all the nodes you need to find is just a prefix of this array. So you make a binary search in this array and find that these are all possible nodes V you need to find. So you just iterate again. What you do? You iterate over all nodes of array D. For each node, you make a binary search and recalculate this prefix. So all nodes in this prefix form a pair with node U. You just need to have a number of these nodes. It's just the index of this node. Yeah. So you can do it in n log n time. You can do it using two-pointer methods, yeah, but you still need to sort the array. So to sort this array, you want to spend n log n time, so you can use binary search as well. So even if you use two-pointers method, you will still need n log n time to sort this array. But if this tree is not weighted, so if all weights of edges are equal, yeah, then you can actually sort it using count and sort, something like that. So if these weights of your edges are all equal to 1, then you can use linear term algorithm. If you have some different weights on edges, then you kind of need to sort this array and spend n log n time. Yeah. Okay. Now, in this problem, we need to make slightly different thing. In this problem, we need to calculate number of UAV such that they belong to different subtrees. There are different ways to solve this problem. First way is to use the following method. We can do it like this. We can use let's say binary search tree to have a kind of sorted array. No, but binary search tree is kind of sorted array. Yeah, you can insert and remove elements in log n time. So we can, instead of this sorted array, we can use a binary search tree, and we can just add elements from left to right. So we will first take the first subtree, add all elements of the first subtree into the binary search tree, then iterate over all elements of second subtree, and find in this binary search tree all elements less than this. Yeah. Now we'll calculate all pairs from first and second subtree. Then we will add second subtree to the same binary search tree. So we will iterate over all elements of this subtree, calculate all pairs like this. Yeah. We will calculate all pairs like this. Then we iterate over all elements of second subtree and add them to the binary search tree. So these elements now belong to the binary search tree. And now we iterate over all elements of the third subtree. So we take element from the third subtree and find in this binary search tree all elements less than this, and add them to the result. So we'll calculate all pairs like this. Now we add all elements of the third subtree to the binary search tree and take fourth subtree and so on. So each time we take the next subtree, all previous subtrees are in our binary search tree. So we take the next subtree and find in this binary search tree all elements less than this. And again, for each element you spend log n time to add element to binary search tree or to remove element from binary search tree. So for each node you spend log n time to calculate the number of pairs. So still you have this time complexity. What is about lecture held in the institute? What do you mean? It's a university course, yeah. If weights are 1, you can also have a bucket of If all weights are 1, you can use buckets instead of this. You just basically you do something like count insert, right? What about nodes in the same subtree? You just not in nodes in the same subtree. You just call recursive procedure for each of these subtree. You call the same procedure, which calculates all pairs inside this subtree. So we have this recursive procedure. You give this procedure some subtree, and it calculates all possible pairs. Now, you have some pairs inside this subtree, so you call the same recursive procedure in each subtree. And then you just need to calculate pairs from different subtrees. And you can calculate these pairs using this method. Yeah. The stream gonna be saved, as usual, in my YouTube channel. Yes. Okay. Another way to calculate the same thing is just by subtracting the values you don't want to calculate. So what you can do is just, no, let's take some node u. So you take some node u, it's here. You want to calculate number of different nodes v, which have d no more than this, and this v belongs to all other subtrees, excluding this subtree. So what you can do is first to calculate all possible nodes using this sorted array, and then subtract the number of nodes inside your subtree. Yeah? Do it like this. So for this node u, I want to calculate the number of nodes v such that the sum is not more than d, and this node v should belong to all subtrees except this subtree. So what I can do, I can pre-calculate this array for the whole, for all possible subtrees. So I make one big array sorted by distance. And for each of the subtrees, I pre-calculate the same small array. A small array for each of these subtrees. And sort them all. Total number of elements is n, so I can pre-calculate all this in n log n time, right? And now I take this node u, I calculate total number of nodes with this distance. It will be the prefix of this array. So I calculate this prefix. And now I just subtract the elements which I don't need to calculate. So I will subtract the elements which are inside my subtree. So I take my small sorted list and make another binary search here. And just subtract this. So I can make plus this and minus this. This little bit more, this is actually easier than it looks. So again, what you need to do, you just, you take some node C, iterate through all subtrees. For each subtree, you just make a defer search test, just iterate through all nodes and calculate the distances. You can make it using simple recursive procedure, right? It's called defer search. We'll talk about defer search in next semester, but that's what it's called. Now you pre-calculate all the distances and form these arrays. For each subtree, you just create this array. Now you sort all these arrays and make one big array and sort this big array. That's all. Now, how to calculate number of pairs? You take the node u, take this big array, make a binary search, count this number of nodes in this prefix, then take your small array, make another binary search, calculate this prefix and subtract it from your answer. That's all. And now you will get the number of possible pairs with paths which go along, which includes this vertex C. Can I implement this code? I think I'll do it in the end. Okay, so the code is pretty simple actually. I will do it in the end. Okay, so should I do it now? No, let's do it later. Just first I will draw some pictures, and then in the end we'll get a lot of pictures, so I will write you some code, okay? First, important thing, right? Important thing is how to choose this node C. So the time complexity depends on how good is your node C, because if you pick the wrong node, you may have a wrong time complexity. So how to pick a good node? Again, when you use divide and conquer technique, you kind of want to split your structure into several parts of the same size, right? Well, basically, when you have a divide and conquer technique on array, yeah, so you want to split it in the middle. So you split it in the middle, you have left part, right part, so t of n will be 2t of n over 2 plus n, so it will be n log n, right? something like that. In this case, we'll try to do something similar. So we will try to pick some vertex C such that the size of these trees will be about n over 2. So the size of all these components will be no more than half of the size of the whole tree. And it turns out it's always possible. Definition. The centroid is a vertex. We'll say that vertex C is the centroid of the tree if we remove this vertex from the tree, the size of each component is no more than n over 2. And now the small observation. It turns out every tree contains at least one centroid. And it's quite easy to find this centroid. So first observation, every tree contains at least one centroid. And second observation, it's very easy to find the centroid. So I will do both. I will show you the algorithm which finds the centroid, and also this algorithm will prove that the centroid exists actually. So how to find the centroid? Let's do the following. Let's pick any node of the tree. So we'll pick any node of the tree. Let's draw some tree. Let's draw something like this and something small. 2, 3, 4, 5, 6. Let's see, 8, 9, 10, 11, 12. Let's put more nodes here. Yeah, good enough, good enough. So you have some tree. You pick any node of the tree, like the one you look first. So you find any node of the tree, and start the depth search from this node. When you start from the search, you calculate the size of each subtree. So you kind of make a rooted tree with with any element as a root, and calculate the size of each subtree. So we start a recursion from here and calculate the let's see, 1, 1, 1, 4, 1, 2, 6, 7, 8, 1, 10, 1, 1, 2, 4, right? It's 15, it's 1, 2, 15 plus 17, 18. Yeah? So you just call a depth search from this root of your tree and pre-calculate the size of each subtree. Now, how to find the centroid? We need a vertex. We know that the size of the tree is 18, right? So n is 18. So let's look on the root of the tree. Let's check if this root is a centroid. No, this root is not a centroid, obviously, because the left subtree is more than n over 2. So this left subtree is more than n over 2. No simple observation. There is at most one child with size more than n over 2. Because if you have two children of size n over 2, then the total size is more than n. Yeah. So you have at most one child which is too big. So let's go to this child. Let's check if this child is a centroid. How to check if the child is a centroid? We will look on its children and see if all the children are less than n over 2. No, it's not, because the left child is more than n over 2. n over 2 is 9, and this left child is 10. So again, we have this child which is more than n over 2. So we go to this left child. Let's take these nodes, check if this node is a centroid. How to check if the node is a centroid? We look on its children and see that both children are less than n over 2. So this is n over 2, and this child is no more than n over 2. And if it is true, then this node is a centroid. Well, why it is a centroid? Well, because for this node, if we remove this node, then all of these subtrees are less than n over 2, and this big subtree, so this subtree is also less than n over 2. Why is less than n over 2? No, because this subtree is more than n over 2. So this is everything except this subtree. So this subtree is more than n over 2, so this part is also less than n over 2. That's all. So that's how you find centroid. If you want to implement this, it's even simple. So let's write some code. So how to write a code which finds this centroid? What you need is to find the node which has I want to make it in one DFS, but I need to calculate the size, right? Let me think. Okay, let's make two DFS. First DFS will find the number of nodes in this tree. Second will find the centroid. Can I do it in one? Let me think. Can I do it in one DFS? Actually, I can if I know the size. If I know the size of the tree. I don't want to say so. Okay, let's make it in two DFS. So first DFS will just find the size of the tree. So let's fade. You can do it with while loop, but still you need to remember all these pointers and remember all these sizes. It's too complicated. Let's make it let's make it simpler. So we'll make first the DFS which calculate the size of the tree. Let's make this DFS1. Very nice names. Okay, let's go. Let's make it a little bit more self-explaining. Let's make the DFS size. So this DFS will just calculate the size of the tree. How to make DFS in a tree? You have your current node X and you have your parent. So you stay in the node X and your previous node is P. So you go here. Now from this node X, you want to go to all possible nodes Y except this node P. And it will return the size of the tree. So it's size equal to 1, then we iterate all possible Y's from the, let's say, G of X. G of X, all neighbors of X. Yeah. So we iterate all neighbors of X except node P. So if Y is not P, when we just call DFS from this node Y, so okay, we'll say S plus equal DFS size of Y. I still try to fit it in 20 lines. Okay, and then just return S. Okay, this procedure just calculates the size of the tree because I need this size. And now, how to find the centroid? Yeah, that's all. DFS centroid. And centroid. Second DFS will find the centroid of the tree. So we'll find just, again, the centroid is the node which have size more than n over 2 and both children have size less than n over 2. So again, we'll do the same. I don't want to save these sizes because I save the memory for some reason. I don't know why. If you don't need to save the memory, you just need you can just pre-calculate all these sizes and save them. I'll just calculate them twice. Again for Y, let's say walk equal to true. Then I'll iterate over all Y's from neighbors of X. I try to save lines, but okay, I will not try to save lines. I'm trying to fit it in 20 lines as I promised, but I will not. Okay, you can do it, but I will not. Equal to df. Okay. if y is not p, then you say sy equal to dfs centroid of yx. Then I calculated the size of y. If size y is more than n over 2, then OK is false. S plus equal sy. Then if s is less than n over 2, then OK is false. Now OK means that my node is the centroid. So my node is centroid if all my children are less or equal than n over 2 and I am greater or equal than n over 2. That's all. So now if I'm centroid, then centroid is x. Return this. Can you spot any bugs? No, looks fine actually. So again, how to use this? How to use this code? You just first you calculate n as the DFS size of let's say node v minus 1, and then you find that centroid of v minus 1, something like this, and now you find the centroid. Yeah, looks fine. Where we're saying it's centroid, we're saying in some global variable. We have global variable. I love global variables. So I will save it in some special variables for centroid. Again, I use the DFS size just to calculate the size of this tree, because I will this is not the size of the whole tree, but the size of my part of the tree. Again, this is recursive procedure, right? So I only work in this area of my tree. So there is some area of my tree where I work, and I want to calculate the size of this small area, and then so n is the size of my area of the tree. And now in my area of the tree, I want to find the centroid, and I use this code to find the centroid. Well, if s is less than n over 2, then I'm not a centroid. Maybe you can skip this. Maybe you can just reassign all possible. No, you cannot. No, you cannot. Again, this check is required to check if so when you remove this node, you have these parts and also this part. So to check that this part is less than n over 2, you need to check that n minus your part is less than n over 2. So this check simply checks that n minus s is less or equal than n over 2. Yeah. So size of this part is n minus size of my part. So it's n minus this part should be less than n over 2. It is the same as s should be greater or equal than n over 2. If s is less than n over 2, then I am not a centroid, because this part is too big. Makes sense. That's all. That's how you find the centroid of the tree. Okay, let's. You can simplify this a little bit. I'm just trying to make a clear code. So this procedure is obviously linear. Yeah. So I can find the centroid of the tree in linear time. Good. And now the whole code. How the whole code looks. It looks kind of the same. So you yeah, I don't like this. I want to remove. What's the problem is I want to remove some nodes. So when I pick this node C, I want to remove it from the tree, and I don't want to remove anything from the tree because it's kind of when you remove the element from the tree, you need to remove all the edges from these lists, and it's complicated. So I will just mark all the nodes which I removed. Let's put here. Let's say if mark X, then return 0, and here like this. Yeah, good enough. So again, I need to skip the centroids I already found. So again, how this code works. I have this tree. Yeah. So that's my tree. First, I find the centroid in this tree. So I find this centroid. Now this tree will be split into several regions. So I have these regions. These subtrees. Now, in each of these subtrees, I will call the same recursive procedure. So I need to find the centroid in each of these parts. And to find the centroid, I want to remove this node C from the tree. Yeah, but instead of removing this tree, I'll just mark this node. So these both DFSs will not go inside this node C. So I'll just mark this node C. And now call DFS from these three nodes. So this DFS will find the centroid of this part of the tree. Again, I will split the tree into some regions. Now I will remove this node, call DFS from these nodes, and so on. So it will still be linear. It's not linear of the size of your current tree, but yes, yes. In this DFS, you will access these removed nodes, but you will access each removed node at most once, so the total time will still be linear. Is it even correct? Let me check. Let me see. Yeah. If you look on the total number of iterations of all these DFSs for all these components, the total time will be linear. That's definitely true. So the total time will still be correct. No, let's write a procedure. So how to find these centroids? We do it like this. So you I need to write some code. Let's say solve for node V. So solve for node V, takes some node V, and solve the problem for the component which contains this node V. So we'll first find the centroid. So again, we'll do this. We'll say n equal to DFS size of V minus 1. Then we'll find the centroid DFS centroid of V minus 1. Now we know the centroid. Now I will remove this centroid from the tree. So I remove this node from the tree and make the same for these components. No, actually in this part I need to calculate the number of paths. Let's calculate. So here you call the procedure which do all this stuff. So you need to calculate all these pairs for this node C. So you do here you do something intelligent, right? So here you actually solve your problem. And now you just call the same procedure for all these. So now you iterate for all nodes U which are neighbors of V and see if not mark U, then you call the safe like this. So again, you take this node C, C. You take this node C, remove it from the tree, now take all neighbors of this node C, and call the same procedure for each of these parts. No, centroid and center is different nodes. We will talk about this in the next practice. So centroid and center are different nodes of the tree. Center is just the middle of the diameter of the tree. So it's a vertex which minimize the maximum of distances to all possible nodes. And centroid is node which splits the tree into equal parts. So it's different terms. So that's basically all. No, okay, it's not 20, but pretty close. Fine. So this is the first type of tasks you can solve using centroid decomposition. Again, what happens in this type of tasks? You need to look on all possible paths in your tree and calculate something. Find the optimal path, or find the number of some paths, or sum of something. So you calculate something among all possible paths in your tree. And you can do it using this centroid decomposition. To apply centroid decomposition, what you need to do is to solve your problem only for paths which includes one vertex. So if you fix one vertex of your tree, and then you can solve your problems for all paths which includes this specific vertex, then you can apply this centroid decomposition technique to solve your problem for all possible paths. Again, what's happening? You take some specific node, which is centroid of your tree, and now you solve your problem for all paths which includes this node. So you find some paths, something like this. What happened? I'm not sure what happened. Something happened. So you fix some node and then calculate all possible paths which go through this vertex C. And now you simply call the same recursive procedure for all these parts. And again, if you can calculate your function for all paths which go through this node C, then you can then apply this divide and conquer technique to solve the whole problem for all possible paths, because all paths are split into these groups. Yeah, let's talk about time complexity. What is the time complexity of this thing? No, let's see. So this part works in linear time, right? This calculate is actually in our approach works in n log n time. So let's use this. And here you simply make recursive calls, right? Now it's about the same as in the simple divide and conquer technique. It's a little bit different because you don't split your set into two equal sets, but it's kind of the same. So let's look. So we have this first recursive call. In first recursive call, we spent like n log n time. So it's n log n time for the first recursive call. Now we split our tree into several parts. So make this part and some small parts here. So we split tree into several parts. For all these parts, we call the same recursive procedure and spend n log n time. So on each layer, we spend n log n time. Now on the next layer, we'll split each of these parts into some several parts again. So we split this, we split this, we split this somehow. Maybe split this. And so on. The depth of this recursion will be at most log n. So we have at most log n recursive calls in this stack, right? So the total time we spend on each layer is n log n. So on each layer of this recursion, total time we spend is n log n, and the number of layers will be log n. So the total time complexity will be n log square. If you can calculate this in in linear time, then total time complexity will be n log n just. Yeah? So if here you have just n, then using the same approach, you calculate the total time will be n log n. It's like always. Usually it's how it works. So if you use some divide and conquer technique, if you can like conquer in some time, then total time will be this time multiplied by log n, because you have log n layers on each layer. This is your time complexity of your calculate function. It's hard to apply master theorem here because we don't split into equal parts. Master theorem is usually applied when you split your problem into some equal parts. Here you split in, split is not equal parts, so it's kind of strange, but it is the same. It is the same. That's all. That's all. So that's how apply centroid decomposition when you have a problem like this. Nice. The second type of problem is a little bit different. In the second type of problem, when you use centroid decomposition, is when you need to answer some requests. So you have some queries, and these queries are something like that. So let me erase something. Can I erase this code, right? I think you will force me to write it again, but okay, I will not write this code again because it's too long. It actually not very intelligent. But I may write this code again later. So the second type of problems is like this. You have some queries on your tree, and queries look like this. Calculate something in the area of some node, something like that. For example, let's solve the following problem. You have a tree again. You have some tree, and you again. I need something. You tell me something you can buy in your area. So what is the idea of the problem? You have requests like this. You are given some node v. Again, let's draw some tree. When I don't know what to do, I just draw trees. Okay, so I will draw another tree. So you have a tree, and you have a request like this. You're given some node v, so you have some node v, and some distance d. Let's say bulk of v, and let's make big d like this. And let's say you're living in this node, and you can travel on distance at most d. So d. So you're living here, and this is maximal distance you can travel. So you can travel from this node on distance at most d. So for example, here, let's say if d equals to 2, then you can travel here, you can travel here, you can travel here, 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 here. So these are all the nodes you can visit if d equals to 2, right? So basically you have some vertex of your tree and some radius. Okay? So you can travel from this node not far from this radius. Okay? And what you want to do is to calculate something in this area. For example, you want to buy something, and you know prices in each node. So each node have some price. Let's see. V is the price of something. I'm not creative enough. Price in vertex V. I have problem with letters V. Vertex V. Okay? Mask? Oh, okay. You still have problem with masks? I don't know. In Russia, you can buy masks like literally everywhere. So they are literally everywhere. It was problem with masks a few months ago, but now it's Maybe because nobody uses them anymore, you know. Yeah. But not so long. Maybe you have just some problem with vaccination. So you may have different vaccination spots in this area. You want to find the closest vaccination spot in this area, something like that. So again, you have it's something like that. You have some area and you want to calculate something in this area, just the closest node, number of different nodes, minimal nodes, something like that. Again, what we want to do, again, in this problem, let's just find the minimal price in this area. So we want to find a minimal price in node U such that distance from V to U is no more than D. That's all. Can you use by heavy light decomposition? No, usually there's different types of problems. Again, in heavy light decomposition, you calculate something on path. So we have path from here to here and calculate some function on this path. In centroid decomposition, you have some area. So you have some node and area around this node, and you want to calculate something in this area. So it's like different types of problems. I actually don't know if there is a problem which can be solved by both techniques. Maybe there is, but it's very different techniques. So no, I can't imagine a problem which can be solved by both techniques. It's very different. So let's solve this problem. Again, in this problem, what we have requests like this. You're given some node and some distance. You want to find all the nodes in this distance from this node V and calculate, for example, minimal price in this area. Is it clear? So what we'll do, we will solve this problem using centroid decomposition. So if you want to answer queries in your centroid decomposition, you need to do some precalculation. So what we'll try to do, we will do all this in the precalculation phase. So we'll first take our tree, run all this recursive procedure, and precalculate these centroids and these areas and so on. I need to draw another tree. Let's draw another tree. Just more space for my big tree. Just to make it interesting, I need to draw a big tree. So I will draw a big tree here. Well, let's go. So we'll have something like this, here, and go here, and something like this, and also here, and this, and something here, and also here. Yeah. Good enough, maybe more. Okay. So you have some tree. Now, if you want to solve it offline, you can do it without precalculation. You can, if you want to solve it offline, it's actually a little bit more easier. But I will answer these queries online. So I have this tree and have this weight fixed, and then I will make some precalculation. And after this precalculation, I will be able to answer these queries online. That's the plan. It actually can be modified to also apply some changes. So if these weights are changed, you still can use the same technique, but not to, you can do it in practice. So I will say that the tree is fixed, all weights are fixed, but these queries are online. So I'll answer these queries one by one. So you have this tree, yeah? So what do? You kind of apply the same algorithm to this tree. You find the centroids, split the trees into groups, find the centroids, split into groups, and so on. But instead of calculating something, you just remember this decomposition. So you take this tree, find the global centroid. What is the centroid of this tree? Let me think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 here. Let's check just here 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 here, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's more, okay. 12, 13, 14, 15, 16, 17, 17 here. So total number is 12 plus 17. So it's 39 and 40 plus 1. So it's 40. So 40 divided by 2 is 20. So this is centroid. Nice. So this node is the centroid of my tree. Now, let's say this is the centroid of level 0. So it's level 0 centroid. So it's the most important centroid of the whole tree. Now, we will split the tree into parts. This part, and this part. Now, in each of these three parts, we will call the same recursive procedure. So we will take each of these parts and find the centroid in each of these parts. I need more colors. So we take each of these parts and find its centroid in each of these parts. So in this part, I think this is a centroid. So this will be the centroid of level 1. So this is component of level 0, and inside this component, there is a centroid of level 1. Now, when you pick this centroid, you will split this component into these parts. So take this part, this part, this part, and this part. Can you see the orange marker? Okay, you can see. Now again, you call the recursive procedure for each of these small parts. So you will find centroid, for example, in this small component, this component of level 1. So this component of level 0, inside this you have component of level 1. Inside this component level 1, you find a centroid of level 2. This. So this will be centroid of level 2. Now again, you split your component into these parts. Now again, you call recursive procedure. Call recursive procedure here. Here you have component of single node. Component of single node is just centroid of itself, right? So this is the centroid level 3. So each node will be centroid of something. Maybe centroid of itself. So each node is centroid of some component. Maybe this component contains only a single node. This is fine. Can there be more than one centroid? Yes, you can have more than one centroid. We will talk about in practice. Sometimes you have two. For example, in this component you have two centroids. So both these nodes can be centroids. So this is centroid of level 3. Here, any of these nodes may be a centroid of this component. So let's say this is centroid of level 3, and this is centroid of level 4. I'm not sure if you can see all the colors I use, but it's a really colorful picture. Okay, if you don't see it, that's kind of sad. But yeah, you kind of see it, but not all of them. Okay. Now in this connect component, in this component, you have this node is centroid level 2. Now you have these parts. Each of these parts is centroid of level 3. In this component, you have, for example, this node centroid level 2, and this centroid level 3. In this component, you have, for example, this is centroid level 2, and now you have these two components. Here you have centroid level 3, here you have centroid level 3, and here you have centroid level 4, and here you have centroid level 4. Whew, that's all. That's the whole decomposition of this component. Now let's move to the next component. So again, for each component, you do the same. You do the same recursive procedure. You find the centroid, split into parts, call recursion for each part. So for this component, which node is, so this node is a centroid. So you pick this node, say this is centroid level 1. Now you split it into parts like this. In each part, you find the centroid and so on. So it's very simple. You just use the same code I just erased, right? So this is level 2, this is 2, this is 2. You have this, and this. I'll just finish this picture because I started. So you don't need to finish this picture if you're trying to remember what's going on. So and in this part, what is centroid? So this is centroid level 2, 2, 2, 2, 2. Not 2, it should be 1. It should be 1, it should be 1. My bad. So this is centroid level 1. Now I have these components, this, and this. Now I find centroid level 2, this is 2, this is 2, this is 2. Now I have these small areas. And each area is a centroid of level 3. Like this. So this is how centroid decomposition looks. It looks kind of scary, but it's not. Again, the algorithm is pretty simple. You take the whole tree, find the global centroid, this, then split your tree into parts. For each part, you call the same recursive procedure. So again, you take some part of your tree, find the centroid, split into parts. For each part, call the same recursive procedure. Find the centroid, split into parts, and so on. Until you have one single node. When you have one single node, it's just centroid, and you have no parts when you remove it. That's all. That's how centroid decomposition looks. Now, how to use it? Is it clear enough? Not too fast, right? Yeah, you forgot to remind me that everything is clear. Yes, okay. Now, let's move back to our problem. So, in this problem, I want to take some node V, yeah, and find some node U such that this distance is no more than V, and then calculate something for this node U. So, how this path actually looks? So, if you take any path in this tree, any path looks like this. If you take this node V and node U, at some point you have some centroid which divides these 2 points into 2 separate groups. So at somewhere here is some node C such that this V belongs to one component and this U belongs to another component. Yes, and they both belong to some big component. So if you look how this decomposition works, so in the beginning, if you take some 2 nodes, let's take some 2 nodes. Let's say this is node U and this is node V. So if you look how your decomposition works, that first you have the whole tree, so U and V belong to the same component. Yeah. Now you take the first centroid and see if U and V belongs to the same component. Yes, they belong to the same component, so you go deeper. Now here you take this centroid, and now U and V belongs to different component. So the path from U to V goes through this centroid. So on the path from V to U, there is always some centroid which belongs to some connected component which belongs to both U and V. So if you take any 2 nodes U and V and look on the path from U to V, this path always looks like this. It goes inside this orange component, yeah, to this orange centroid. And now from this orange centroid to this orange connected component. So all paths in a tree looks like this. So any path, if this path belongs to some component, this path goes through the centroid of this connect component. Now, how to find all possible? So we have node V and we need to find this node U. So instead of finding this node U, we will iterate for all possible nodes C. So we know this node V, we will iterate through all possible C. So node C is centroid of some component which contains node V. So there is at most log n possible centroids. So there is at most log n possible nodes C. So we'll iterate through all possible centroids. And for each centroid, try to find all nodes U which like this. So again, we know node V is node from our requests. Now we have node V. We will find the node C. Node C must be a centroid of some component which includes node V. So the first centroid is actually node V. Node V is centroid of itself. Actually, C0. Let's see. So node V is centroid of some component. Let's see like this. So it has some nodes. You have some components here. So no, every node is a centroid of something, maybe of itself. Let's go. Now first let's calculate the answer for this component. How to calculate answer for this component? Well, it's pretty simple. We need to find all the nodes inside this component with distance no more than d. Again, what we will do, we'll take all the nodes inside this component, sort them by the distance. So we take all nodes of this component, sort them by the distance. And now what we need to do is to find the prefix of this array. So we find prefix of this array. So these are all possible u's such that distance from V to U is no more than D, right? And for this prefix, we just need to find the minimum. We can pre-calculate minimum for each prefix. So we take all nodes in this component, put them in one array, sort this array by distance, and then calculate the minimum for each prefix. We can do it in linear time. We need n log n to sort it, actually. Yeah, you can make a persistent segment tree instead, yeah. There's always possibility to make a persistent segment tree. If you know how to make a persistent segment tree, you always can do it. no, actually not. Persistent segment tree is quite dangerous to use because it uses a lot of memory. So if you want to, if you can avoid using persistent segment tree, you actually want to avoid it. Array is much more efficient. So if you can use sorted array instead of persistent segment tree, that's a good plan. Now, so that's the first centroid. Now you take the next centroid. So you take the centroid, which is on the next level. So you take this next level centroid, C1. So you have this node C1. It has several components. Where is this? Now, if node U is here, then this sum of distances should be no more than this. So distance from V to C plus distance from U to C should be no more than D. Again, we know this distance. We know this distance. This is just distance from V to the centroid. We can pre-calculate all distances. So we'll pre-calculate distance from V to the centroid. And now we just need to find all nodes U such that distance from centroid to U is no more than D minus distance from centroid to V. So we know this part should be no more than D minus distance from C to V. Again, how to find all such nodes? We can do it in the same way. We will take all these components. This all is component of this centroid C1. So for this whole component, we will take this node C1 and pre-calculate distances from this C1 to all elements in this component. Put them into array, sort this array, and now we just need in this array to find some prefix. Again, in the same way, we find this prefix. So these are all possible u's which satisfy this inequation. Yeah. And then on this prefix, you just need to find the minimum. Okay. So you make a binary search, find this prefix, find the minimum on this prefix. You calculate. You find all possible nodes U in this component. Now you take the next centroid, do the same, and so on. So on each level, you take the centroid and find all the nodes which have distance from this centroid no more than this. This is some prefix of this array. You take this prefix, find the minimum on this prefix. You're done. You just do it on each level of your decomposition. No, easiest way to implement this actually is the following. For each node V, you can pre-calculate the centroids for this node V. So for each node V, you can pre-calculate the array of all centroids of these nodes. You can do it on pre-calculation phase. So when you build this decomposition, you can remember for each node all the centroids of this node. You don't need to build this tree of centroids. It's too complicated. You still use n-log-n memory, so it doesn't make sense. So for each node, you just can pre-calculate the pointers to all possible centroids of this node. And in this, when you answer the query, you just iterate through all centroids of nodes V. So it really will be the array of pairs, so centroid and distance from V to this centroid. So you have array like this. For each node, you have array of all centroids of this node. So let's take some node. Let's take this node. For this node V, yeah. So this node will be the first centroid. This node be the second centroid. This node be the first centroid, and this will be the fourth centroid. So you start from here, take this centroid, calculate something here, go here, calculate something here, then go here, calculate something here, then go here, calculate something in the whole tree. Again, you can pre-calculate this array on the pre-calculation phase. It's quite simple. You can do it. You can do it in the same. You need to write another DFS to calculate this, but you need 3 DFSs. Okay. You write another DFS which iterates over all elements of your component, and for each node in your component, you just put this pair into list for this element. That's actually quite easy. And now, in the end, here, when you answer the query, you just iterate over all these centroids just using for loop. You just iterate over all elements of this list. And for each centroid, you know this distance, and you want for each centroid find all elements in this prefix. So for each centroid, you store this array of all elements in this component, sort these arrays. No, this takes some coding skills, but it's actually not that complicated. So when you pre-calculate this array, everything else is quite simple. So for each centroid, you maintain the list of all elements inside component of this centroid. You sort this array by the distance, make a binary search. So it's a lot of code, but it's actually quite easy code. So all actions are actually quite simple. There's nothing sophisticated, right? It's like no like bit magic or something. So all actions are pretty simple. So you make this recursive procedure, pre-calculate this. Now you pre-calculate these arrays, sort them, make binary search, and so on. So all steps are pretty simple. How to iterate for centroid? Again, you can pre-calculate for each node all the centroids of this node in the pre-calculation phase. So when you build this decomposition, you can make these lists. So for each node, you will maintain lists of all centroids of this node. Again, how to do it? When you build your decomposition, you find this first centroid. Yeah. So you find the first centroid. Now you iterate on all nodes of your tree and put this centroid into lists for each node. So you take all nodes in your tree and in each list put this centroid. Now you call recursion here. So here recursion, you take this centroid. Now you iterate on all elements in this component and put this centroid into all these lists. And so on. Each time you take centroid, you find centroid, And then you call the procedure which adds this centroid into all elements of this component. It's another DFS. So you call DFS from this node. It iterates all nodes of this component and adds this centroid into the list. No, you may look at this as a tree. So if you look on these centroids, how they this inclusion tree of this component. So if you start from this, so you have this component and component inside of the component and so on. So if you look, you may look on it as another tree. You may build a tree of these connect components, but you actually don't need this. Usually you don't need to build this tree explicitly. Usually if you just need to answer queries like this, you just need lists like this, and you don't need to build this whole tree of centroids and what centroid is inside what centroid and stuff like that. Yeah, in some problems you may want to build this tree, so you want to see that these centroids have these centroids as children, something like that. But usually you don't. Usually you just need these lists of all centroids of the given node, and that's enough. So when you need to answer the query, you just iterate over all centroids. For each centroid, you calculate something. When you don't know distances, when you don't know this, you can pre-calculate distances. Yeah. For each centroid, you can pre-calculate distances to all nodes inside this component. You can do it in the same procedure. So when you, in the pre-calculation phase, when you find the centroid, you can start from this centroid and find distances to all nodes of your tree and save them somewhere. It's actually not a problem. We only consider distance from the centroid to some node inside the component of this centroid. And we can pre-calculate these distances. We can, for each node, we can pre-calculate distance to the centroid. These are n log n values, right? For each centroid, we find the distance to all vertices inside its component. So total number of elements is just n log n. So we can pre-calculate these n log n values, and we only need these n log n values. We never try to find distance from one node to another node. We only take care about distances from node to the centroid. And for each node, we have only n log n centroids, so we need only these n log n values. We can pre-calculate them before. All pairs shortest path faster log n in normal graphs? I don't think so. It depends on graph. We'll talk about graphs next semester. No, in trees, in trees, yes, in trees you can. No, in trees you can obviously pre-calculate all distances in n square time. So you can run DFS from each node and pre-calculate distances to all other nodes in linear time. So if you have tree, you can pre-calculate all pairs of distances in n square time. But we don't want to spend n square time here. We want to spend n log n time here. So all this pre-calculation works in n log n time here. And that's kind of important. So if you don't want to spend n square time anywhere, because n square is usually too much when you have big tree. Okay. Yeah. So that's about minimum. Again, we will have the same problem as before. When you have minimum, it's not a problem, but if you want to calculate sum in this area, it's kind of different. So what happens if instead of minimum here, I want to calculate sum of all elements here? Just sum. Or maybe just number of elements. If I want to find the number of nodes in this radius, that's kind of different. Again, by the same reasons as before. Because here, I want to calculate number of nodes u in all trees except this node v. Yeah? So I want to find number of nodes u such that this distance is no more than this, and this u shouldn't belong to this subtree, right? So if you have something like this, so if you want to calculate instead of minimum, you want to calculate, when you have minimum, it's not a problem. When you have minimum, you just calculate some vertices twice. So you want to, again, what's happening? You find the minimum in this area, and in this area, right? So you find all nodes such that the distance from C to U is no more than this. These are these nodes. But these nodes are already calculated. So you calculate these nodes twice. It's no problem when you have minimum. When you have minimum, you can calculate the same node twice, and it is the same because it is an idempotent function. Yeah. But if you have sum, you cannot do it like this. Yeah, because you calculate this node several times. So to fix this, you do kind of the same trick as we did before. So you calculate this sum and then subtract sum inside your subtree. So you take your subtree, recalculate the same sorted array for your subtree only, and then subtract this prefix from the result. So the total number of elements the sum of all elements in this area will be a sum of all these elements minus sum of your elements. So you take all these elements, then subtract these elements. So when you subtract these elements, you will get the correct sum. So it's the same trick as before, but you kind of need to apply it before. So you first make this centroid decomposition, build all these arrays, sort them, and so on. No, in trees you can find distance in constant time. You can find LCA in constant time and find distance in constant time. So it's not a problem. Yeah. If you have something a little bit more complicated, so again, if you have minimum, you just ignore this problem. If you have sum, you can subtract. If you have some function which is not inversible, so if you have function when you can subtract. That's complicated. One of the most universal techniques looks like this. So you want to again, you have this centroid, you have these components. Let's have 4 components. This have V, and you want to calculate something on all elements except this component. So you want to calculate something in these subtrees, but not in your subtree. What you can do, you can put all these elements into single arrays, so like this, and split it into regions like this. And now what you want to do is to calculate function in all array except this segment. So you want to, in this array, you want to calculate function in this region. So you want to be able to calculate some function in the array when you remove some segment from this array. How you can do it? You can pre-calculate your function for all prefixes and for all suffixes. So you can pre-calculate function for this prefix and pre-calculate function for this suffix. And now when you remove your segment, you know this answer, you know this answer, you just add these 2 answers and you get the answer on the whole array except this segment. The problem is that usually you don't want to just calculate some function. Usually this function depends on this, so you need some data structure like this sort of arrays. Yeah. So you have some data structure which answers your queries, right? So you kind of need data structure for each prefix and data structure for each suffix. But if you can make persistent data structure, then you can make persistent, like for example, if you need to build a binary search tree for each prefix, you can make persistent binary search tree, add elements 1 by 1 from left. So for each prefix you will have a version of your persistent binary search tree. And for each suffix, so for each suffix you will have some version of your persistent binary search tree. And now you have this binary search tree, this binary search tree, you calculate this answer, in the end you will calculate your final answer. That's the most common technique. It's kind of complicated, but usually you don't need something like this. Usually you have something like minimum or something like sum. If you have some minimum, you just ignore it. If you have some, then you can subtract. Usually this covers most of the cases when you use this technique. But if not, then you might think about something like that. But usually you don't need to. Okay, that's all for today.